All right, hello. We are here. We are going to learn about the first and second derivative tests. So some things that you need for this, you need a spoon. That's for the second derivative test. You need some sort of spoon. This is a really big spoon, which you need a spoon. And you need some sort of thing that you can show is like going up or going down. I have this really fun little penguin, but you could use anything really. But you know, stuffed animals are fun. All right, let's try it. So, derivatives and curves. We have the first derivative test and the second derivative test, and we are going to talk about how our first derivative can tell us about the shape of a graph, and how the second derivative can tell us about the shape of a graph, and how we can utilize our understanding of points, critical points, to also figure out, with our understanding of derivatives, what the classification for those critical points could be. So that was, what were the names for extremas? It was local mins, relative mins, those are the same. Local or relative max, absolute or global mins, absolute or global maxes. So that's the plan. So, here we have a function that is increasing. The function is increasing here, which means that our first derivative is greater than 0. Because as we are stepping to the right, our function's going up. This is something that you also, I think, went over in pre-calc. I mean, like going up, right? That's what's happening here. Our first derivative is positive. And then once we get here, what's happening? The function is decreasing, so our first derivative is negative. And then at b, our function starts increasing again, so our first derivative is positive. So you get your little thing that's going up and down, showing your slope. So we have positive slope for f is less than a. We have a negative slope for when f is between a and b, and we have a positive slope when x is greater than b. Oh, sorry, I messed up all the language. So we have x is greater than, when x is less than a, f prime of x is positive. When x is between a and b, f prime of x is negative, because our function is decreasing. And when x is greater than b, f prime of x is positive, and our function is increasing again. So, if we know that our derivative is positive, then we can say that our function is increasing on the interval where our derivative is positive. Similarly, if our derivative is negative, then we can say that our function is decreasing over the interval where our derivative is negative. So what happens when those change? When we change from going from a derivative that's positive to a derivative that's negative. Here we have our function is increasing. Change that so my head's not in the way. Okay, so here we have our function is increasing, right? It's going up. Wait, I went the wrong way. Here we have the function is going up, and then at that point, our derivative is undefined because we have like this sharp turn, so we can't take the limit of our slope. And then our derivative is negative. So at this location right here, what do we have? We have a maximum. Is it a local or is it a global maximum? We're not sure yet. At a quick glance over our entire graph, it looks like it's local. But, you know, it could just be the scale. So here, when we go from increasing to decreasing, our derivative goes from positive to negative, then we have a local maximum. Similarly, when we go from a decreasing interval to an increasing interval, and we have a critical point here because our derivative equals 0, so that's our definition of a critical point. A critical value is the x value that we plug in such that the derivative at that x value is 0. And the critical point is the location. So this is the critical point. The critical value is b. So there we have, when we go from a negative derivative to a positive derivative, then our function has a local minimum. So now we have an increasing function, so our derivative is positive, and then our derivative is 0. And so this is a critical point. C is a critical value. But then our function continues to increase. So what can we say about f prime? What can we say about this location? It was a candidate for being an extrema, but it is not an extrema. Interesting, interesting. And then here, right there, we have our function is increasing because our slope is positive, our derivative is positive. And then at D, f prime of D equals 0, so we have a horizontal tangent. And then to the right of D, f prime is negative, which means our function is decreasing. So now that we've talked about this motion, this increasing and decreasing motion and what happens, let's formalize it in what's called the first derivative test. And I need a pen and my finger penguin. This is a, I would put this at a 3. I can't draw stars with a penguin on my finger. It's a really bad star. It's about a 3-star theorem because this is extremely useful in justifying how we classify our critical points. So, suppose f is a continuous function over an interval I containing a critical point C. If f is differentiable over I, except possibly at C, then f of C satisfies one of the following descriptions. So all that to say, we have a function, it's continuous, and so our penguin can like slide onto it, our tangent penguin. But you don't know if it's differentiable everywhere because it could, at this critical point, we could have an undefined slope, like a sharp turn, and that's okay. So if f prime changes sign from positive, which means that our function's increasing, when x is less than c, so that's to the left, to negative f prime when x is greater than c, then f of c is a local maximum of f. And the motion here is going up, and then we have something, either a undefined derivative or a 0 derivative, and then changes to negative, so it's decreasing on the way out. Then we have a local maximum. If f prime changes sign from negative, so decreasing, when x is less than c, to positive, increasing, when x is greater than c, then f of c is a local minimum of f. It's decreasing to increasing, that change gives us a minimum. But if f prime has the same sign for x is less than c and x is greater than c, so increasing, and then we have something happening here, and then we have increasing again, then f of c is neither a local maximum nor a local minimum. You could also say relative maximum or relative minimum. And the same goes, like, so increase and then you stop and then you increase again. That's not an extrema. Decrease, then you stop for a little bit and then you decrease again. Not a local extrema right there. But if you're going from increasing to decreasing, positive derivative to negative derivative, then you have a local maximum. If you have negative derivative to positive derivative, you have a local minimum. It's a mountain or a valley. So how can we use the first derivative test to find all of our local extrema for f of x equals the cube root of x minus 1? And just so that we're all remembering, this is what the cube root kind of looks like, and then it's transformed a little bit. So this might be a terrible question. So we have this function, it's continuous, right, because it's never undefined, and we don't have any jump discontinuities or anything like that, so we can use the first derivative test. That's good. So we need f prime of x equals 1/3 x minus 1 to the negative 2/3 power times the derivative of x minus 1, which is just 1. Hey, Ms. Contreras, how did you get that? Well, we have cube root of x minus 1 is equal to x minus 1 to the 1/3 power, and then we power rule that, so the derivative is 1/3 times x minus 1 to the 1/3 minus 1 power, because we reduce our power. We need to reduce this power by 1. So 1/3 minus 1 is negative 2/3. So we get negative 2/3 right there. Whoops. Okay, so to find our critical values, we need to figure out when this is undefined. So maybe we should rewrite this as 1/3 times x minus 1 to the 2/3 power. Sounds good? All right, so this is undefined when x equals 1, right? Because when our denominator equals 0, when does that happen? When x equals 1. And when is this equal to 0? When is this whole thing equal to 0? F prime of x, that was a really weird x, equals 0? Never. All right, so our critical value is x equals 1. So we need to classify x equals 1. What kind of extrema is it an extrema? I don't know. Well, what if we plug in a number? So if we plug in a number, let's say less than 1. So we have 1. What's a number less than 1? I think 0 is a nice number less than 1. So f prime at 0, and what do we get? We get 1/3 times 0 minus 1 to the 2/3 power. So we do, this is 1/3 times 1 to the 2/3 power. Well, we got an even in the numerator, so that becomes just a positive 1, and the cube root of positive 1 is still 1. So we get 1/3. Okay. So we have 1/3, and that's greater than 0. So that means that f prime is greater than 0. And then at 1, our f prime is undefined. And then greater than 1, what's going to happen? F prime at, I don't know, let's go with 2, is 1/3, 1/3 times 2 minus 1 to the 2/3 power, and that's again 1/3. So f prime of x is greater than 0 again at 2, which means that according to the first derivative test, x equals 1 gives us f of 1. So the point 1 f of 1 is not a local extrema. We have found a failure of the first derivative test. So now let's think about, and this is a vocabulary that might be familiar to you, might not be, but that's okay. So if we have a function f that is differentiable over the open interval I, if f prime is increasing over I, so if we have our little penguin and then its rate of change is going up, then what's happening to it? This penguin is like blasting off into space. Then f is concave up over I. So that means that if our first derivative is increasing, then our function is concave up. And concave up, another way we like to think about it is, can it hold like soup or ramen or something tasty? Is it a spoon facing upwards? Concave up. If f prime is decreasing over I, so the rate of change is going down, then we say f is concave down over I. F prime is decreasing, f is concave down. So see the penguin, it's going down. Its rate of change, the slope of this penguin is becoming more and more negative. So this is concave down. This is concave up with the spoon facing upwards, going up like this, and concave down when our function's slope is decreasing. Concave down. Some people like to write concave up with a smiley face because the smile is concave up, and then concave down is like a frown. That's another way people like to remember that. So there's a lot of vocabulary, and so this is a nice way of like looking at it. When we have f prime is increasing, then f is concave up. So we have an increasing function, and we have our derivative is increasing, right? Because the slope here is not as steep as our slope there. Then our function is concave up. We have f prime is decreasing, so that means that our function is concave down. So here we have, but we still have f prime of x is greater than 0, and f prime of x is greater than 0 here. So this is f double prime is greater than 0 because our f prime is increasing, and here we have f double prime of x is less than 0, which means that our f prime is decreasing. Down in the bottom left, we have f prime is increasing, and so f is concave up. However, f prime is less than 0. So this is the shape when f double prime is positive, our second derivative is positive, and our first derivative is negative. And bottom right corner, we have f prime is decreasing, and f is concave down. So this means that f prime of x is less than 0, and f double prime of x is also less than 0. Concave up and increasing is both first and second derivatives are positive. Concave down and decreasing, both first and second derivatives are negative. Concave down and increasing, first derivative is positive, second derivative is negative. And concave up but decreasing, first derivative is negative, second derivative is positive. So here's we just said that, sorry. Let f be a function that is twice differentiable, so we can take two derivatives of it. That's what twice differentiable means. Then if f double prime is positive for all x and I, then f is concave up over I. Concave up. Hold cereal or whatever else you want to hold in a spoon. And if f double prime is negative for all x's in the interval I, then f is concave down over I. Concave down means it does not hold water. Concave down is a frown. So, if f is continuous at A, and f changes concavity at A, which means that f double prime changes signs at A, then the point A, f of A, is an inflection point, or point of inflection. Point of inflection, which is sometimes endearingly referred to as POI, or P-O-I. There's a couple other things that are POI or P-O-I. This is one. It is mashed taro. It's okay. It's okay. It's not super flavorful. It's all about the other things you're eating with it. And this is a cool video about fire poi. Can we? Oh, is it embedded? Oh, that's so cool. So, yep, pretty cool. You can feel free to look at that on your own. Okay, so we talked about the first derivative test, where if our function was increasing and then decreasing, then we had a maximum. If our function was decreasing and then increasing, we had a minimum. And if our function was increasing and then increasing, or decreasing, then decreasing, then we didn't have any local extrema. But the way we talked about it was using the first derivative, right? So the first derivative is positive, and then the first derivative is negative, and then we had a maximum. If our first derivative is negative, and then our first derivative is positive, then we have a minimum. And if our first derivative does not change signs, then we don't have a local extrema. So that's the first derivative test. The second derivative test is another justification for what the classification for extrema can be. So if we have f prime of c equals 0, and f double prime is continuous over an interval containing c. So that means that our derivative is 0, right? We have a critical value. And it's a critical value specifically that we still have a second derivative. Because in order to have a second derivative, you need a first derivative, right? So if our first derivative is undefined, then you can't take a second derivative of that. So we need f prime of c equals 0, that kind of critical point. If f double prime of c is greater than 0, what does that mean? Concave up. So if our function is concave up, then f has a local minimum at c, right? That makes sense. If f double prime is negative, that means that we have what? Concave down. Then f has a local what? Maximum at c. If f double prime at c equals 0, then we don't know. Because if there's no concavity, then, you know, like what's an example of something that wouldn't really work there? If we have our, if we had a function, this is a bad sketch. If we had a function that goes like this, and then we just like flat plane for a while, and then we go up again. Look, f prime equals 0 for all of this. But f double prime also equals 0, because the derivative of 0 is 0. So then, like, what's happening here? No. So, let's consider this function. F of x equals x cubed minus 3 halves x squared minus 18. We are given that the points c equals 3, so our inputs, I don't like this grammar, the values, c equals 3 and negative 2 satisfy f prime of c equals 1. We need to use the second derivative test to determine whether f has a local max or a local min at those points. So, how do we use the second derivative test? Well, we need to make sure that f prime of c equals 0, so we are given that. So we need to evaluate f double prime. And how do we do that? Well, we got to take two derivatives. So let's take one derivative. Derivative of x cubed is 3x squared minus 3 halves times x squared. 3 halves times 2 is 3 times x to the first power minus 18. And f double prime is a derivative of f prime, where 3 times 2 is 6 times x. So we got 6x minus the derivative of 3x is 3, plus the derivative of negative 18, which is 0. So, this is a line. Line. I can spell line. The second derivative is a line. So the second derivative is going to look something like this. I don't know. The first derivative is a parabola. So the first derivative is going to look something like this. Is that? I don't know. Maybe. But that makes sense, right? That we have a cubic function whose first derivative is a quadratic function and whose second derivative is a linear function. Okay, let's erase that. So we need to use the second derivative test to determine whether f has a local max or a local min at c equals 3 and at c equals negative 2. So let's just plug it in. F double prime at 3. What is it? 6 times 3 minus 3, 18 minus 3, 15. 15 is greater than 0. So that means that our function is concave up at c equals 3, or at x equals 3. Concave up means that we have what kind of extrema? What is that? It's a minimum. So by the second derivative test, since f double prime at 3, that was a bad 3, f double prime at 3 is greater than 0, then f, the point 3, f of 3 is a local min. When c equals -2, we have f double prime of -2 equals 6 times -2 minus 3, and this is going to give me a very negative number, right? Minus 3. Oh, it's just -15. Huh. So that means that my function is concave down at x equals -2. Concave down means what kind of extrema do I have? I have a maximum. So by the second derivative test, since f double prime at -2 is less than 0, the point -2, oh, I can't write, the point -2 comma f of -2 is a local, wait, it was negative, right? So concave down, so local max. I just imagine a spoon every time I'm doing these. All right, so there you have it. First derivative test and second derivative test. Those are both used for justifying, classifying, and then justifying what kind of extrema we have. The first derivative test and the second derivative test are not about increasing, decreasing, or justifying if something is concave up or concave down. Those are definitions. The first derivative test and the second derivative test are tests for classifying extrema. So, that about does it. I'm just gonna, I don't have a good sign off. Maybe I should work on that. Let me just look at the penguin again. All right.